Good day, students. Welcome to our another online session for the course Computer Organization. And this session is specifically designed for the students of BEE 7A. And we're going to continue our discussion, which we stopped in the previous discussion while we were discussing the processor and its internal architecture. And we're basically going to design the single cycle processor. Till now, we have discussed about the basic structure of a single cycle processor, and we've seen that how the instruction cycle is processed, and then we're going to modify that basic structure depending upon the needs and requirements of our instructions. So, in today's session, basically, we will be discussing the logic design basics that are being used in order to design the processor, and what are the combinational component or combinatorial components that are being implemented in our processor, and what are the sequential or the state components of the elements that are being implemented within our processor. Basically, our processor contains both combinational and sequential logic, and basically sequential logic basically helps us in managing the timing information and coordination and the sequence of operations which we can perform by using the single cycle processor. So to start our discussion, first of all, let us see what are the logic design principles which we will be following. As we have discussed that uh, the basic information that will our processor will gonna process is basically in binary. If you remember that while we were discussing the machine code formats for all the instructions, and we have discussed that how the instructions are encoded, and what are the bit representation of the instructions, and what is the significance of those bits in order to encode any particular instruction, or how we're gonna implement that, basically what that instructions decoded in set of logics or hardware or processed by the hardware. We're going to extract those information that is being provided within that machine code, and then we're going to process our information on a single cycle processor. So the first important thing is our information which we need to process in a single cycle processor, that is in binary. That is basically the machine code, and that machine code represents basically depending upon the implementation technology. The low voltage represents the zero state or the logic zero, and the high voltage represents the one state. So what in terms of voltages, that is dependent upon the implementation technology. For example, if you're using the TTL technology, that is the transistor logic technology, in order to implement our design, then the definition of 0 and 1 is defined as per that standard. But if you are using some other standard, for example the CMOS standards, by CMOS standards or some other standard, then definitely the definition of 0 and 1 is represented according to that standard. So basically 0 represents the lowest range, 0 belongs to the lowest range in that range distribution, and 1 belongs to the upper range or the highest range. And what would be the maximum value? For example, for the TTL, if we have to define 0 and 1 with respect to TTL, then we can say that from 0 till 2.2 volt, we've got, if you got any voltage within this range, if you got any voltage within this range, then that is treated as the logic 0. This is basically the logic 0 for the TTL standard. And from 3.3 volts till 5 volts or 5.5 volts, if I have to use the upper range, that is basically 5.5 volts. That is basically the VCC plus 0.5 volts. So we can also represent in the 5 volts as well. So that is basically, this is the range that basically represents our logic 1. So as far as the definition of bits and the hardware components are concerned, basically the number of bits we represent one wire per bit. So basically we are transferring one bit on a wire. So if you represent one bit, basically in a circuit we have to use a wire basically to carry out that information from one node to another node, or from one component to another node to another component. So this is basically one wire per bit, and multi-bit data encoded on multiple wires or buses. So if you've got to 32-bit data, we have to encode 32-bit data, then we have to use 32 wires basically, and we represent that in terms of buses. Then we've said that our system is being distributed into two major components. One are the combinational components, and another are the sequential components. So our combinational logic or the combinational component modules basically that operate on data, and basically uh, they represents the output is basically the function of inputs. Whatsoever the number of set of inputs that are provided to the hardware, our output is dependent upon that, and function defines what we are going to do with that inputs. And for as the state or the sequential elements are concerned, that are basically used to store information or basically use to implement the control unit that is used to control our the basic operations of our processor. Now coming to the combinational element, if we have to represent the AND operation, then we have to use AND gate, and then adders are represented in this representation. You can see that this is the adder of the two inputs A and B, and Y is the output. The size of the A and B can be the single bit, or in our diagram that can have A and B can represent the buses that can carry multiple data, and Y is basically A plus B in this particular case, and the size of Y is always one greater than the size of the inputs. Now coming to the multiplexer, how we're going to represent that into the expression basically. So y is equal to s basically depending upon uh, these are the two inputs, and in this particular case we've got I naught and I1. These are the two input lines, and s is a selection criteria basically that basically used to select when y has been assigned I naught and when y has been assigned I1 basically. So this is a conditional expression here, and if that condition if is been satisfied basically, if s equals to for example if x the value of s, let me write it. For example, I've written here that if s equals to 0, then in that particular case y equals to I naught, and else y equals I1. Okay, so we've got some multiplexers or multiplexer modules are there in our system. Then we've got some arithmetic and logical modules. For example, our ALU. So ALU will receive the inputs A and B and are the inputs. Y is the output, and this F basically is are the control lines, control signals. You can say that these are the control signals that basically defines that which sort of operation our ALU is performing, and that is dependent upon the instruction itself. So basically this F is being generated by the control unit depending upon the instruction, and this ALU basically is a combination of the hardware modules that can consist of adders, subtractors, multipliers, logical components of the modules that are also included in the ALU. So this is just a block representation, uh, and the operation that is being specified by the ALU is being specified by the control unit, and control unit basically specifies the operation depending upon the operation code that has been received from the instruction memory. Now coming to the sequential elements, so for the sequential elements we have to we're using registers in order to store data in the circuit basically. So registers are the sequential component that are basically synchronized with the clock element. Either we have got a synchronization with the positive edge of the clock, or we have the synchronization with the negative edge of the clock. And if you see this timing diagram here, basically the system is synchronized with the positive edge, and whatsoever the value of D is on a positive edge, that has been latched to the output. That has been latched to the output on the positive edge only. So basically it uses a clock signal to determine when to update the stored value, and it's the edge triggered system updated when the clock changes from 0 to 1. So this is a positive edge triggered system in this particular example. And if the system is negative edge triggered system, then our transitions are done on these edges if we've got a negative edge triggered system. And in our diagram we have to represent a bubble here in order to represent that the system is synchronized within the clock negative edge rather than the clock's positive edge, right? So sometimes we do have some sort of controlled element that are included in our system to enhance the control of or we can say that to enhance the operation or in a much coordinated way and a much controlled way. For example, we've seen in a digital circuits we've got sometimes the enable or input in order to enable or disable the operation. We've got here in this particular example we've got this write control signal, and its value basically determines that when we're going to write the value to the output or not. So in this particular case we can see that if this write is active high enable, then whenever the value of write equals to the 1 and the clock equals to the 1, so only on that particular instances we're going to write the data to the queue. Okay, now what would be the clocking methodology which we will use basically? Combinational components don't require the clock, but the sequential components do require the clock element in order to operate in the system. So combinational logic transforms during the clock cycles between the clock edges, and input from the state element and the output to the state element basically that have been determined, and longest delay determines the clock period basically. So basically we have to see in a data path that what is the longest delaying path basically existing in a combinational logic module. So that basically is known to be the critical path. We will going to define that. So critical path basically exists in the combinational modules, and how we're going to reduce that? Basically, we have to introduce the registered components in between that logic in order to break that path to enhance our clocking requirements or the clock latency basically. Now, how to build a data path? Basically, a data path consists of the elements that process the data and addresses in the CPU basically. So all those hardware elements basically that are used to process our data and addresses in the processor, that is known to be a data path. And we will discuss the single cycle MIPS data path, that is single cycle data path, and we're gonna define or refine our design incrementally with each step according to each instruction, and we're going to see how what are the changes that are being required in order to implement that particular data path. And now in our previous discussion we have said that we have to perform the series of operation in order to process the instruction cycle, if you remember that. So the first step is in order to process the instruction we have to fetch the instruction first, and from now the most important question is from where we have to fetch the instruction. Basically we have to fetch the instruction from the compartment or the memory module that basically contains the machine code base of the program basically. And in the MIPS architecture of the single cycle processor, we've got the instruction memory basically that is responsible to hold the machine code. If you remember the x86-64 architecture, the memory is segmented memory, and if you remember that the code segment is the dedicated segment that contains the machine code of our program, and we're going to access that with the help of the code segment registers and instruction pointer basically that provides the machine code through the bus interface unit into the instruction queue, and that has been later been processed by the execution unit in the processor. So same is the case here. We've got the machine code that has been stored in instruction memory, and these are the components, these are the basic components of the modules that are being utilized in while fetching the instruction. So if you see that the basic it consists of the three major elements. The first element is a program counter, that is simply a counter that provides the addresses of the instruction to be fetched. The compartment itself from where we have to fetch the instruction, and that is instruction memory, and the adder that basically generates the next instruction address. And we have to increment this by 4. If you remember that the instruction memory is the byte oriented memory, and our machine code basically in order to store a word we have to have the 32 bits data in order to store in the instruction memory. We have to utilize 4 uh, uh, dedicated locations in order to store a machine code of one instruction. So the next instruction machine code will definitely be the 4 incremental away from the base address. So we have to add the 4 in the current address in order to generate the next address of the instruction in a normal flow of execution, which later on we will see how we're going to change that. So these are the major components that are used for the instruction fetch. Then we've got some register files here. Register file basically is a compartment uh, that provides us the content of the registers that are being included or being utilized in the instruction itself. So these are the interfaces for the register file. Uh, this is a control line basically that has been generated by the control unit. Then we've got read register 1, read register 2, write register, and write data. If you remember that in our machine code, the terms that have been appearing as RS, 5 bits RS, RT, and RD basically. So those bits basically are being mapped here on these dedicated lines. Then if you have to write the data into a register, we have got a 32-bit interface here that brings the data back to the register. And the address is being specified by this, or we can say that RD. And operands are read here. For example, if we have to read the value of RS and RT, we provide the addresses here, 5-bit addresses or the location addresses, and the data that within that locations are being provided here. So this is 32-bit, and this is also 32-bit. Similarly, the ALU process the input that is also 32 bits. And this is also the signal that is being generated by the control unit. So these are the primary interfaces that are being provided with the registers and register file or the ALU. And we've discussed in our physical classes the internal structure of a register file in detail. That we've got 32 dedicated register, we've got 2 multiplexes there, and one decoder there in order to decode the addresses. And we've seen the mechanism of reading the registers and writing the registers while we are attending the physical classes in detail. Similar is the case with the ALU as well. Then for the load store instructions, we've got the memory compartment that is basically in order to deal with the data references, that is a data memory. Similarly, these two are coming from the control unit. One for the memory read, when we have to read the memory, we have to enable this signal, and one for the memory write, and when we have to write something in the memory, we have to enable this signal. Basically, these are the control signals that are being provided by the control unit itself. And sometimes we require the sign extension process to convert the data from the 16 bits to 32 bits. We will discuss that in detail. Why will you use sign extension process? Because for any arithmetic operation, the sizes of the data must be same. So in order to make the data sizes same, we have to extend the data. So we use sign extension units for that purpose. Well, that was all for today's discussion. We will continue from here. And we will go to the complete data path, and we're going to modify that for the R format first, then I format, and J formats and branches, and then afterward discussing those concepts, we're going to switch to the pipeline processor. Till now, take care, have a good day.